Write an expression for the nth term of the sequence. This first example, we have a sequence of fractions, 3/4, 4/5, 5/6. Recall that your first term needs to coincide with a sub 1. When you build your nth term, 3 is 1 plus 2, 4 is 1 plus 3. Now the numerator is always smaller than the denominator by 1, so they only need to differ by 1. But since we start with 3, 4, 5, 6, instead of 1, 2, 3, and 4, we need to take into account that our starting number of 1, we've got to add 2 to get it to start properly. And you can check this term. If you do a sub 1, you get 3 over 4. A sub 2 would be 4 over 5, and it checks out. This would be your nth term. In the second example, we have a list of numbers: 3, 2 plus a half, 2 plus a third, 2 plus a fourth. Notice that what we're adding to 2 is always a fraction with a growing denominator. This number 3 out front, could we write 3 as 2 plus 1 over 1? Does that equal 3? It does. So we can make the claim that our nth term is 2 plus 1 over n. Starting with a sub 1, that would be 3 as our first term. A sub 2, 2 plus 1 half, that is our second term. A sub 3, 2 plus 1 third, that's our third term. So we have the right nth term written down. The next example, we have 1 over 2 times 3, 2 over 3 times 4, 3 over 4 times 5. The numerators follow the counting number order, 1, 2, 3, 4, and so on. The lower left number was always 1 more than the numerator, and the second number in the denominator is always 2 more than the numerator. So we have numerator, the first number was 1 more every time. The second number was 2 more than the numerator every time. So that's our nth term for that sequence. Determine whether the sequence is monotonic and or bounded. In our first example, and I think we've investigated that sequence, the nth term, before. Let's let n get really large. If you take the limit as n goes to infinity, plus 3 doesn't really matter. 7n over n, that reduces to 7 over 1 when n gets really large. You have matching powers of n. So as n goes to infinity, we have a limiting value of 7. We have a convergent sequence. When you plug in a 1, 7 over 4, that's 1.75. Plug in a 2, that's 14 over 5. That's 3 and some change. Plug in a 3, 21 over 6. It turns out that the values, as n increases, the value of this fraction increases. So you get an increasing list of numbers. They increase in size from one number to the next. So since that happens every time, this is monotonic, and bounded, turns out bounded above by 7. And you can check this. If you write out 4 or 5 terms like A1, A2, all the way to like A sub 5, and you write out the values, you'll see that your values always increase. And we have a cap on how far they'll go. 7, it turns out, would be the largest possible. The second example, 1 over n, this nth term approaches 0 as n gets really large. Starting with 1, 1 over 1 is 1. Moving up to 2, we'd have 1 half, and then 1 third, 1 fourth. The values of the sequence consistently get smaller and smaller. So that's monotonic. We never have a fluctuation. The numbers always get smaller the more numbers you list. If you were to write like the thousandth term, 1/1000th, that's getting really close to zero, super small. So this is a monotonic bounded sequence. Our third example, we did this one in class also. We have n squared over n plus 1. Now, since the numerator has a more dominant power than the denominator, this nth term will approach infinity as n goes to infinity. It's not bounded. In fact, when we wrote out some terms of this, starting with 1, we would have 1/2, move up to 2. 2 squared over 2 plus 1 was 4/3. 3 squared over 3 plus 1 was 9/4. These values consistently get larger every term, and because that limit is not bounded by a fixed number, they would just keep getting larger without restriction. The next example, n over e to the n over 3 power. Let n go to infinity. We'd have an infinity over an infinity. So this one qualifies for L'Hopital's. We have the indeterminate form infinity over infinity. Remember, n's getting really large. Take the derivative of the numerator. That gives us 1. Take the derivative of the denominator. That's e to the 1/3 n times 1/3. Don't forget chain rule. Dividing by a third is the same as multiplying by 3. Now, when n gets really large, we have a fixed numerator, an increasingly large denominator, so that limit goes to 0. However, we put this into our calculator in the y equals screen, and we went into the table and saw that at first the sequence values increase in size, but then they start tapering off and decreasing. So I made a note here that if you were to investigate, say, the first 5 or 6 terms of this sequence, at first your values start getting larger and larger, but you reach a point where they get smaller and smaller. Now, since it's not consistent one way or the other, not monotonic. But we do have a limit of 0, so that tells us that it's a convergent sequence. A sub n equals -1 to the n. It's bounded because the graph can never escape 1 or -1, but it's not monotonic because depending on whether n is odd or even, that lands you at positive or -1.